for chapter 5, normally I used to divide it into two sections, but I think maybe the second section it's maybe too short. So I'm gonna combine everything together, and then I'm trying to finish it within 2 hours. Okay, so we're going to save some a week for the tutoring again, like similar to the midterm. Okay, so that will be really helpful for you before your final exam. We talk things about final exam. In final exam, there's no written examination, but there will be in total of 100 multiple choice questions for 2 hours, right? So but it's a little bit different from midterm exam because you guys will be finished everything like your lab testing, your lectures. So there will be some short calculation question. I think maybe about like 30 of it, but it's going to be really easy, but it's going to be really random. It can be from your lab testing, so I may give you guys your lab because I'm going to capture your data from the laboratory testing that you upload in SUT e-learning, and then I'm going to convert it and then maybe put it in the examination, and you guys need to convert. So you guys must know what you guys have done, right, since the day one. For example, like for lab number 1, I may put some equipment like the maybe UTM or whatsoever, and then I'm going to ask you what is this machine called, stuff like that. Okay, and the second question for the lab number 2, it can be like maybe give you guys some numbers in order to calculate for Poisson ratio and stuff. So it's not gonna be like really hard derive the equation, but you guys just need to know, maybe need to write down some equation on the one sheet again. So I'm going to provide you again one sheet. So to get full benefit of one sheet, you guys can just write everything's calculation or maybe formulas that you guys think that it will be essential for you for the final exam. You can just write everything. You can just write small, because it's really beneficial, for you guys. If you guys write less thing, which mean you guys need to remember a lot, but if you guys like write a lot, so you need to remember less. So I encourage you guys to write a lot on the one sheet. You can just like divide horizontally. I think one of you guys like did it pretty well in the midterm. So you just divide it and write down all the chapters and then divide it clearly. So it help a lot, in the midterm. Okay, so please do it similar. Please do it again for the final exam. Okay, so that's why I don't want you to leave early. You need to check, like recheck it again if you have time. If you double check it already, so that's fine. You are good to leave. Okay. All right, coming back to our chapter 5. So chapter 5 basically use the knowledge from chapter 4. From the chapter 4 is about the mechanical properties of the materials. So we're going to, after we know the mechanical property, we're going to check back on the characteristic of the test. Okay. So in conclusion, for this course, we divide it into 5 main testing. We have one is tension. So what are the material that we test for tension? We have rubber, right? The rubber we test for Poisson ratio. We have rubbers. We have what else? We have steel. We have cast iron. We have what else? Did we pull out the aluminum? No. We have cast iron, just only the iron. Steel, iron, steel is DB12, I guess. Okay, after we test it, we draw stress strain curve. Okay, and then we're going to find the mechanical property and stuff. Okay, so you guys may have noticed we need to find ultimate point, yielding point, and percent elongation, and lastly is going to be the modulus of elasticity for the tensile. But for the rubber, we tested for the Poisson ratio only. Okay, and second one is going to be the compression test. What are the materials that we test for compression? We have, first one is going to be concrete. We have concrete. We have what else? Brick. We have another one is timber, or just call it wood or timbers. It's okay for both of it. Okay, so it just like a basic one. So you press it, get the final value final value, and then find the stress. Okay, and then we have another test. We call it shear test. Have you learned shear test? Not yet. Okay, so in shear test we basically divide into tests. One is the double shear test, double shear, and another one is single shear. Double shear we test with the brass, coppers, and aluminum. Okay, the question is, why don't we test for the steel? Okay, because steel is going to be really ductile. Okay, when we test it for the shear test, most of the time it's going to elongate a lot. Okay, it produces plastic hinge, so that's why we don't test for the shear test for the steel, so it's not gonna fail. Okay, and then another one is the single shear. Single shear you test for the wood, right? If you remember, there's a wood like this, and you apply like this, and then there will be some shear occurs inside, and then we can just find shear stress equal to force that you apply P over the area. Okay, pretty simple. Another one, I think, flexural test and bending. This one missing, and bending. Flexural test or bending test. Okay, in bending test we test a lot for the wood. We have cast iron, and then we also have the another one is the iron, the ductile steel. Okay, and then for this we just like put it into the machine, right? And then just put it like this, and then we're going to bend it by applying point load over here, and then measure the deformation at the maximum. Okay, after the load reduce, and then we can plot the deformation F and force and deformation curve, and then it's going to look like this, and then for the brittle it's going to look like this, and then fail over here. And lastly is the one you have test already, is fatigue, right? So you have test fatigue for what material? For aluminum, right? So just only one material that we test is the aluminum. Okay, for the fatigue test it's going to be we saw the result that it's when it failed as brittle material. All right, so today's class we're going to review on everything's again over here before our lab on the next class. So this can be in the examination, you know, I may be asked how many tests in the lab, like for all the labs that we do in the laboratory. So how many tests? You can just I may ask you 5, 4, 3, 2, 1. So you can just pick 5 for 5 of these. Okay, all right, move to the point number 1. We're going to talk one by one, go through the tension test. I think tension test it's going to be really simple and straightforward, because tension test you're going to pick the material like this, and then you just like pull it, and then you know the area over here is going to be your A, and then you pull it by P over here. So the stress is going to be P over A, and the strain is going to be again delta divided by the original length, or L0. Okay, and then you're going to get strain. Kind of straightforward. Okay, but again, if I ask you in the examination, we have like cold form and the hot roll, and then the cold roll or cold form steel. For the hot roll from TIS 1227, this one is going to be a hot roll, and then the cold form is going to be TIS 1228. This one is cold form. Okay, so just differentiate it. I may ask you either one of these in the exam, so you can just like answer me the TS. Okay, all right, so this one I'm gonna go really quick because we talked like main things about this already since the midterm. So we have first one, we have when we test the tensile, of course, we're going to plot the stress strain curve. In the stress strain curve, we have like how many points over here? 1, 2, 3, 4, 5, 6, 7, 8. 8 points that we're going to consider, or maybe 9 is modulus of toughness. Okay, so basically we have 1 point is the proportional limit is point number 1, 2, 3, 4, 5, 6, 7, 8, 9. So this one is going to be point number 1, and yielding stress is going to be the lower yielding. Again, do not use the upper yielding, so this one is going to be the point number 2. The ultimate stress is going to be point number 3, where slope equal to 0. And then fracture one is going to be number 4 over here. And number 5 is the percentage elongation. So you need to observe here and then calculate like this. And then number 6, area of the reduction. So you need to measure the diameters, the final diameters after testing, after it failed. Okay, the final diameters, and compare with the original diameters. Okay, so it's going to be the final. So you can just find the area reduction. 7 is modulus of elasticity is going to be the slope in linear region, which E equal to delta just write down as PL divided by strain PL. It's also okay. Or if you want to make it as a really linear, it's going to be delta sigma over delta strain. Modulus of resilience is going to be the area under the linear zone. Okay, so this is going to be the area. Let me highlight it. Okay, this is the modulus of resilience. It's going to be the area under the linear region, and then it's going to be the last one, modulus of toughness, going to be in here, between half of the area between the ultimate and the yielding. So if you would like to get the equation, you can just go back and then recheck it later. Okay, and then if we look at any steel catalog, for example, like the SYS, which is the company under SCG, you can see that they normally like specify like yielding stress, ultimate stress, percentage elongation, and modulus of elasticity for you. For example, like this. Okay, for the hot rolled steel over here from TS 1227, if you remember from engineering material class, you will know if you would like to produce some structural steel like this, if you remember, they tell you the formulas in order to form the steel. Okay, for example, like the Cu whatsoever, if you mix it, you're going to produce this kind of steel. Okay, and then if you look at the specification or mechanical properties of the steel, for example, like if I pick SS 490 for the thickness that less than 16 millimeters, I'm going to have the yielding stress equal to 285, and then the ultimate stress minimum at 490 over here, sigma ultimate, and this one is percentage elongation, and then the energy capacity. And lastly, it's going to be the modulus of elasticity. They may have stated in the first page that all of their steel going to have the minimum of modulus of elasticity equal to 200 gigapascal over here. Okay, so this is how we read it. Next is going to be the question that frequently asked, that how can we know that which material tests for compression or which material we're going to test for the tension? So basically it depends on your usage. For example, like metal. Okay, metal, most of the time we're going to use it to resist tensile force. Okay, so when we use it to resist tensile force, most of the time we're going to test for tension. We're going to use tension tests. Okay, for example, like the steel brick over here. Okay, the question is, can we construct this using the concrete brick? Of course, yes. But if you remember the equation from the uniform stress, the maximum deflection is going to be 5 WL force over 3 force EI, right? So if we use concrete, the EI of concrete it's going the E of concrete, Young modulus of concrete is about like 200 KSC. But for the Young modulus of the steel, it's going to be approximate 2 million KSC. So it's going to be still going to produce like 10 times better in stiffness. Okay, it's going to produce 10 times better in stiffness, which means it can reduce 10 times of the deflections. Okay, if you compare it. So if you look at the application, when the train runs on this bridge, which means it will produce the tensile stress on the steel members like this tensile. So when it produces tensile stress, what happened? We're going to test the steel that's subject to the tensile load. Okay, so we're going to get its properties. And for compression, it's going to be really straightforward. It's going to be the one that going to resist the axial load, for example, like columns like that, and then you have like the wall also resist some vertical loads, and then that's why we test for compression. Okay, like column or walls, because of its material too that can resist a lot of distress. Okay, move next to the wood or timbers. So the timbers, they're just like 2 point different of the timber or wood material. It's just like parallel to the grain and perpendicular to the grain. Okay, for example, if we compare tensile test to the grain and then compare with the compressive strength to the grain, shear strength to the grain, you can see that the tensile going to produce a really high resistance strength, which means when we test it, we need to look at the application first. And if we look at it, we can see that from these figures, okay, there will be some load subject to this point. And then if we draw a free body diagram, you can see that there will be some force that going to produce in y-axis, and then this one is going to produce in x-axis. This force going to produce shear stress to the wood, and then this one is going to produce compression stress to the wood. Okay, so most of the time timber, it can be subject to the tensile, but rarely fail by the tensile. So that's why most of the time when we test for the timbers, we would like to test for compressive strength parallel to the grain, perpendicular to the grain, and then if we test for the shear, maybe both parallel to the grain and perpendicular to the grain. Okay, so for the wood, we not gonna we rarely test for the tensile, but we're going to test for the compression test and shear test instead. Okay, similar to here. Okay, if they drill this and then they insert the connection over here, the wood most of the time fail by shear. Okay, like this block, this shear block over here. Okay, another point is the installation of specimen into the testing machine. Have you wondered why don't we put the concrete and then just pull it like the steel? If you have that question in mind, so I'm gonna so this slide is going to answer your questions, which are the concrete itself. It has the interlocking between stone and mortar. Okay, so what happened over here is if you grip it top and bottom, since the tensile force of the concrete is going to fail about like 5 to 10% of the compressive strength. So when you grip it, the force that's going to push or acting to the concrete is going to break the head of the concrete specimen. Okay, so that's why we cannot grip it. If we grip it, we pull it, it's going to fail at the top or the bottom first. So that's why we are not gonna test it for pulling. Okay. If we compare it to the steel, we cannot do it similar to the steel because steel is really good at compression. So if you put the apparatus over here, the grip over here, the head grip over here, so there will be nothing happen to the steel. Okay, and it's going to elongate at the middle according to the theory. So it can be used, but for the concrete, we need to do something different. So if you would like to find the tensile strength of the concrete, we need to test a test called splitting tensile test over here. So what is the test for splitting tensile? We're going to put the concrete over here, and then we're going to put the vertical load on top of the cylindrical sample of concrete like this. And then we're going to apply the uniform load to our concrete specimen over here. So the load transfer is going to run in this figure. When we transfer it, it's going to transfer like this. And then the reaction is going to run to the center of the sample like this. Okay. So what happened over here is this blue one is going to be the action. And the reaction of the concrete itself is going to try to resist this. And then lastly, it's going to break apart into pieces like this. So the stress that it tried to react to the action force is going to be the tensile force. Okay. So lastly, you're going to get the force P from the monitors after you test it, and then you can just like calculate by using the area of the inside area over here of the specimens. Okay. All right. So we'll see in the next slides. And then next one is going to be the specimen. So for the specimen in our lab, I think we have two of this. One is shoulders and one is threaded end. So the reason that we use this type of the threaded end and the shoulder end because of just only for easy to install. So it's easy to install compared to the other type. Okay. And then for the specimen, you can see that we're going to have some increment. Increment means increase in section, which means we would like to make the stress, okay, to transform uniformly, okay, or we call it stress transformation uniformly, which means we force the sample to be failed in between this area. Okay, if you produce the sample that's going to be having similar site, sometime it's going to fail at the gripping point over here or the end of the sample over here. So we don't want it to happen. So we want it to happen to we want it to fail or happen to fail at the middle of the specimen. So that's why we increase the section at the end. Okay. All right. And then some defect specimen, for example, like type A, B, C, and D. So this can be in the exam. So I'm going to ask you, maybe I maybe give you the one of these figures, okay, about center line. So I'm going to ask you what is the defect of this specimen. So you need to answer just only the center line of reduction section and the end parallel, but do not coincide over here. So it can be like this in the examination. And then we have four types. One is not in the centers. One is similarly not in the centers. Second one is not symmetry for sample number sample C. And then Sample D is going to be the defect of the sample, which some part of the material is missing out, which means the area resistant area is going to be missing. Okay, it's going to be smaller over here. When you pull it, it's going to fail at this point. Okay, so it's not a good specimen for testing. And for the specimen that we test at the lab, for example, this cast iron, we use the standard of ASTM E8, and then we use this side as the large one. Okay, this one is for the cast iron, and for the steel, we use this one. Okay. All right. So coming back to the splitting tensile test for concrete, this one, you can see that we cannot pull it directly as a steel. We cannot pull it like this. So one way that we can convert for the splitting tensile is just to apply force over here, make it fail, and then measure the reaction force of the concrete cylindrical concrete over here as P, and then we can just calculate it easily by equal to 2P over pi LD, where L is going to be the length of the sample and D is going to be the diameters of the sample over here. Normally, the ratio of the cylindrical concrete sample is going to be 1/2, which means 1 in diameters and then 2 in length. Okay, there's 1 L. All right. Okay, so in the examination, I may ask you for this for the tension test. Okay, what lab are we going to test for? Okay, so you can just I may give you choice similar to what you have done in the midterm. C, D, maybe labs 2 and 3, or maybe E, all. So just answer all over here. Okay. All right, it's going to be like this. All right, so if you test it for the tensile, there are some few important note that you need to also keep in mind. For the first one is going to be the defect of the specimen. You need to note it in the report. Okay, if there's any defects, and type of the testing machine. So you need to observe the capacity. Sometimes when the sample is too big and then you test it in a small machine, it can be broken the machine. And then speed of the test, you can just read it from the standard. Okay, right now we use the machine, okay, in order to get a constant standard. But for our lab, Ajahn Sitichai would like you to feel the test by yourself. So that's why we still have like the manual machine. Okay, but that manual machine is going to produce a lot of error. Okay? Because one sample you're going to apply really slow and another one is going to be really fast. So the speed of test is going to matters on the testing results. And the main part over here is going to be this one. Okay, for example, like the behavior of material at different region. I think last week before midterm exam, you learn about tensile test, right? Am I right? Of steel. So people may ask you to control the load by two methods. One is going to be load controlling. The second one is going to be displacement controlling. So for the load controlling, we're going to control it for brittle material. Brittle material. Okay. For the displacement controlling, we're going to use it for the ductile material. Ductile material. Okay. But for our labs, for the steel, for the iron that we test at the lab, the small one, we need to use the combination between load controlling and the displacement controlling, because of the in the zone of the linear region. Okay, if we use the displacement control, it's going to take really long. So that's why we allow you to use the load control during the elastic region first, and then when the load drop comes to the yielding point, and then we let you test as the displacement controlling instead of the load controlling. And for the brittle material, we're going to test just only one method using the load controlling. But right now, like in the automatic machine, like for example, like F1, that machine does not care about like the behavior of material because it kind of really in detail, which they're going to test everything using displacement control. But displacement control is going to be the best one if I can choose between load controlling and displacement controlling. Okay, we're going to see later what are the difference and the mode of failures over here. So here we go. Here's the load controlling versus the displacement controlling test. So for the load controlling, for example, like this, when it become like yielding stress like this. So at this yielding point, for example, if I tell you guys to test at every 1 kilonewton, right? So when it drop over here, the displacement still runs, but the load is not increasing anymore, which means you miss some dial gate point over here. So that's why load controlling is not really good for the ductile material. But for the displacement controlling test, you can just like measure whatever force by your default displacement. Okay, for example, like people say that you need to measure at every 10 division. So 10 division you read the load, 10 division you read the load every 10 division. So you're going to get all exactly the behaviors of the material. Okay, right. But in our lab, of course, we use manual. We need to combine between load controlling and displacement controlling for the steel. Okay, and there we go. Here are the failure type of the sample over here. So when you write your report, so you need to state this one. Okay, what type of failure is that your material experience? So it can be flat, cap cone, partial cap cone, or star fractures, or maybe irregular fibers. And then last one is going to be cap cone silky, but most of the time you're going to experience A to E, okay, not F. So you can just write it down. So this one is going to be the perfect one for the tensile. This one, cap cone silky, and this one is perfect one for the cast iron. Okay, if it shows something like this, maybe you can just write it down as the partially cap cone. Maybe the material maybe not homogeneous. Okay, so that's why it failed like that. So you can just state it like this. So for the failure of the tension test, you can just note it in your report or write the conclusion by using the apparent cracking patterns and also the fine of course. Okay, depends on your material. All right, and then factors affecting the tension test. Most of the time it's not gonna occur for the tension, but it occurs for the compression. So do you know what is eccentricity? Have you ever heard about this term before? No, right? So the eccentricity means, for example, if it's like when we test the material like this, we're going to put the force at the center line. For example, this is your sample, right? I compress it at the center. You know what happened? It's going to be just only P over A, right? If you would like to get the stress. Okay. But what if I move my hand over here to a little bit not in the centers like this? So there will be some overturning occurs, which means when I put it at the middle, nothing happened. Okay, like this. But if I shift my load to over here, okay, so there will be some movement occurs. Okay, so this length, for example, if this remote like this, so this one is my bottom fingers, is the reaction over here. But if my top fingers point over here as P, which means I produce some length over here, I call it E length, which means it's the eccentricity length, which means the length that different from the center line. Okay, so what happens when there's some eccentricity occurs to your sample? If you look at here, you can see that if the sample, okay, if this is the same sample and then without eccentricity length, for example, if it's normal, if you put some, I need to erase this first. Okay, there's no moment occurs here, and then the reaction force at the bottom of the steel over here is going to be uniform. Okay, which means the stress over here is going to come from F over A only, or P over A only. Okay, but when there's some eccentricity link as shown in these figures, you know what happened? This one is going to be stress at the bottom over here. Stress max is going to be P over A plus moment multiplied with the Y divided with the I, which means there will be some stress that occurs by the moment, where the moment comes from the eccentricity link multiplied with the force. Okay, which means if there's some eccentricity link during the installation of the testing, so it's not gonna provide the exact force or stress, because it's going to fail faster. Your sample is going to fail faster. For example, if there are some eccentricity link occurs on your sample, it's going to fail at this point first. Okay, which means sigma max is going to occur at this. Okay, and next one is going to be the test speed. So the test speed, if you test the same sample, you need to remain with the test speed, and the test speed can be observed by ASTM or TIS. Here it is. So they state the rate of testing. You can just read from that, which the test speed for the ductility is supposed to be lower than the sample that brittle. Okay, and over here is the failures according to the tension. This one again, we have talked already from the previous class. So if this one is tensile and this one is the ductile material, ductile, subject to tension, and then if you pull it, it's going to fail as 45 degree, and then this one is going to be fail as according to the shear. And this one, brittle, which is the cast iron brittle, you pull it out by using tension test, the angle of failure is going to be 90, and it's going to fail by tension. Okay, simple as that. And then the cast iron is going to have the plane about like 90 degree. Okay, and again, this one is just the example. For example, if this is the column, and then the column subject to the compression stress, so that's why we test the concrete in this cylindrical sample. And then for the tower crane, of course, it's also subject to the compression strain. And then for the truss over here, it's supposed to be compression on the top and then tensile at the bottom. Okay, so you're going to learn it later in the design class. Okay, I think that's about it for the tensile. Do you have any question so far? If not, we're going to move to the static compression. So we just finished tension, and then we go to compression. In compression, we have concrete is the main one. Second one is going to be brick, and lastly is going to be the timber or the wood. Okay, so for the compression material, we're going to consider 3 points. We have, but we can find 5 points, but we focus just only 3 points. We have yielding compressive stress, ultimate compressive stress, and modulus of elasticity. Okay, so for example, like this, for compression stress, if you ever test it at the lab, you need to place the concrete cube, the concrete cylinder sample, at the middle of the machine. Am I right? People is trying to let you observe the machine and then make sure that the sample is going to be at the centers. Okay, so what happens if the sample is not at the centers? Which means it's going to produce some eccentric link to your sample, right? So if this is the force P, Okay, the force P is over here, and then the center line of the machine is over here, and the center line of your sample is going to be over here. You know what happened is you're going to produce the eccentric length E over here. So your concrete sample is going to experience the stress that come from P over A plus the My over I, which means you guys going to produce the maximum stress at the toe over here, and then the testing result is not gonna be exactly as what we wanted in the objective. Okay, which means it's going to be less than the real behavior of the material. Okay, so this is the eccentricity. This is the effect from the eccentricity length. Okay, next one is going to be the buckling. Okay, so the buckling of the sample, we also in the lab we don't test for the compression of steel. Okay, because the compression of steel, it's require a really high capacity of the machine, and then the sample is going to be really small. If we extend the steel sample to be long, like in this sample steel, the thing that it happened is it failed by buckling. Okay, it's not failed by sample really small. Okay, so we'll see later in the next slide. And then it usually, if you would like to get the exactly material behavior of the steel, so it's really expensive. So that's why it's not really that famous to test for compression strength of the steel. Right, and for the concrete, okay, so when we test for the concrete in the lab, what we need to consider is the surface frictions. Okay, and over here, this one also cause some error in your compression force when you test at the lab, which when you test it, if the surface is not really flat, what you guys need to do is you guys need to put the plaster. Okay, the white one that you mix with the waters and then put it on the brick, so that's what we call plaster, the white one, and then you guys need to make it dry and then make it flat. That's not all. If you would like to test for the compression strength of the concrete, you need to have the cap over here. Okay, or we call it capping of the concrete over here, in order to make sure that the sample is going to be level and then can be applied the force directly from the machine through the sample. Okay, this is how we test it. We need to add plasters to make the surface flat for both sides. Normally at the bottom, it's okay, because when we cast it in the mold, at the bottom is going to be flat automatically, but at the top, some of you may need to write something like group 1 or group 2, so which means the surface is not going to be flat. Sometimes you need to cut the surface out. Okay, but this one is supposed to be in the ratio of 1 diameters and 2 of the diameters in length. All right, for the compressive strength of the steel, you can see that from the ASTM E9. This may be asked in the examination, so I may ask you, to prevent buckling, what are the height of the material that for the steel that we need to have? So I may give you choice H approximately 8D to 10D, or maybe 9D to 11 or 10 to 12, whatsoever. I'm going to put it in the examination, so you guys need to answer me the correct one, which means the sample is supposed to be not higher than 8 to 10D, which D is the diameters of the sample. Okay, and to reduce the friction, the one that we have just talked, F mu n over here, so we need to make the sample not to be shorter than 2h. Okay, so from this one slide, I can ask like for 2 questions. So most of the time, you can see that the compression of the steel is going to be in this length. So this one, I may provide you these figures and then ask you which one is the appropriate length of the compression of steel for testing without having buckling and the friction. So you can just ask the medium length specimen over here. Okay, so it can be asked like 3 questions from one slide. Next one, the mold that we use at the lab, the cylindrical one, this one comes from the code from ASTM C31 and TAS 409 that they said that the diameters of the cylinder is supposed to be like 3 times of the aggregate size. Okay, for the aggregate size, it can be goes up to 2 inch. Okay, where 1 inch it's about 2.5 centimeters, which means if you substitute it in here, it's going to be 3 multiplied with 2 inch, it's going to be 6 inch, the diameters. So 6 multiplied with 2.5, oh, 1 inch, 3, 6, okay. So it's approximately 15 centimeters, okay. So that's why you can see that our mold at the lab, so the cylindrical one, we have the size of 15 centimeters by the depth of 2 times of the diameters to prevent the friction, which is 300 millimeters or 30 centimeter. This one, 6 inch or 150 millimeters for the cylindrical sample. Okay, so the largest aggregate that we use maybe 51 millimeters, but most of the time we're going to use just only about like 1 inch of the aggregate for the stone. All right. All right, so this one you must be kept before testing. All right. Similarly, if I ask you what lab that we're going to use for the testing in compression, you need to ask lab 5, 6, 7. Okay. All right, but there will be one question that I usually use for the to ask student is when I was in the lab, so I always tell them that the machine that can be used is just only 80% of its capacity. For example, this compression machine. So this is going to be having the capacity of about like 2000 kilonewton. So the actual use, I may ask in the exam that what is the allowable capacity of 2000 kilonewton UTM. Okay, so you guys need to remember that you can use just only 80% of the capacity, which means if I ask you here, so I may give you try like 1 kilonewton, only 160, maybe 2000 or 5000. So just use 0.8 multiplied with the capacity of the machine, which is 2000. So it's going to be 1600 over here. Right. So this, like for this one, if you use the FC prime of the concrete equal to 280 KSC, so it's approximately P of the 280 KSC. It's just only about like 500 kilonewton, I guess. So it's okay to use this 2000 to use this 1600 allowable capacity. So it's okay to use for this machine. All right, so for the observation in compression, nothing much. What I want to focus is just only the cast iron. You can see that the cast iron is going to provide similar Young modulus in both compression and tension. This one is tension, this one is compression. Okay, so it has similarly linear elastic region, which going to provide similar volume of the Young modulus, and the cast iron is going to fail properly when reaching its tension. So when you pull it, it's going to break apart by tension because of its micro crack, okay, inside. All right, but when you test it for the compression, it's change its behaviors. Okay, it provide a lot of deformation before it fail for the cast iron. All right, so this is the material sample that we talked that this one is going to be the D, and then this one is going to be the 3D. The medium side one to avoid the friction and also avoid the buckling. And this is the compression of the cast iron. It's going to fail 45°. And for the aluminum alloy, it's going to fail also 45° over here. And you can see that why don't we test for the steel? The thing that happened over here is the steel is not gonna fail like this. Okay, so there's no fracture point for the steel when we test for compression. It's going to have something called Poisson effect over here. So the Poisson effect means the material itself is going to expand its area. So over here, you may not learn in this class, but you're going to learn it in soil mechanics lab. Okay, so we're going to talk about it, and you're going to meet me at this lab. So we're going to test and then try to calculate for the correction area for the Poisson effect. Okay. All right. So for the hot rolled steel, so I may ask what is the shape of the hot rolled steel under compression. So you can just answer it as like a barrel over here. Okay, and the concrete, it's going to actually concrete is supposed to be fail at 45°, but the thing happened is because of the failure itself, it has some concrete stone and the interlocking between stone and the mortar itself. So sometimes you cannot get it exactly 45. It can be 50 to 60 with the vertical line if you compare. Okay. Oh, so this one is going to be concrete. Let me start this one. Okay. All right. So for the brittle material, sample like concrete, we have three type of failures. For example, if it is like a cubic sample like this and cylindrical sample like this, like two of this, we have three type of failures. In examination, I may provide you this image and then ask you what is the failure of this image. So the failure of this cubic sample is going to be shear cone or the hourglass shape. Okay, when you test it, this one is going to break down to the side, and then what is going to be left over is just only the hourglass over here, or the shear cone. We call it shear cone. And the second one is going to be shear plane, like 45° like this. For example, like this, it's going to be in this plane. And the second one, it can be like go down here and then break apart, and then just left with the modern shape like this. Okay, so we call it shear cone with vertical crack, and this one is shear plane. So when you write down in your report, you can just report it by using the different characteristic of the failures over here. So you can just follow this and then write in your report. All right, so again, the concrete cannot be fail exactly at 45 because it's a non-homogeneous material. Because in the concrete we have stone, we have like mortars that are the liquid to bond between the stone to form concrete, so it's not homogeneous. Okay, so that's why it fail in 50 to 60° most of the time. And the friction of the surface of loading head and specimen can be occurs. Okay, so we need to cap it first before we test it. Otherwise, it's going to fail by the combined stress layers. Next one is going to be the timbers under compression. So timber under compression, it's depends on it's parallel to the grain or it's going to be perpendicular to the grain. So if you test it perpendicular to the grain, which means your sample is going to fail by crushing. For example, if you remember from the lab, you have a wood like this, you put a metal plate at the bottom, and this is the grain. Then you put another plate on top, and then you try to apply some load over here. P. When you apply some load over here, so the sample is going to crush and then it fail as crushing. It's going to look like this. And then you can just write down in your report. And then we have many type of failure of the compression. For example, if you put it vertically like this, for example, if the grain is not gonna be like straight as what we want it can be diagonal like this. So when you apply the force, so it can be fail like diagonal according to the grain of the steel, grain of the wood, sorry. And then it can be failed by shearing, but not really much often seen. But for the one that usually see is the splitting, when you test it parallel to the grain. So this one is going to split the grain, because the grain is like a piece of it's like a plate, you know, just like put it together. When you press it, and if one plate cannot be resist, it's going to try to push to our side. Okay, so it's going to fail like this by splitting out like this. Okay. All right, next one is going to be compression and shearing parallel, and then the brooming or at rolling, which mean the it has no grain, and then it's really hard on the top, so that's why it's going to fail at the top of the sample. So we call it brooming. Okay, so 2 point to be remembered is just only when the timber is subject to the compression, when it perpendicular to the grain, it usually fail by crushing. And another point is when it subject to compression in parallel to its grain, so it usually fail by buckling of the timber grain, causing the rupture of the timbers. Okay, so this can be in the exam later. Please be noted. All right, and next, is going to be 5.3 is static shear. So the static shear over here we consider is, for example, from this image, we have this one as the tie rod. Okay, so this one is the tie rod, and then we try to pull this bowl. Okay, we try to pull this bowl, which we can draw the free body diagram of the bowl over here as this. Okay, we have tie rod over here, full in force P from tie rod. Then the surface between the connection over here is going to be the direct shear occurs to the bowl. Okay, so the shear over here is going to be equal to P over 2. This one is going to be P over 2 similarly. Okay, so from this point, you can just like find this one, we call it the double shear. You can see that in our CE field, normally we're not gonna use like a single shear. We usually use a double shear because it can save the material. Okay, if we use single shear, it's not really that economical for the practice. So this one is double shear. Okay, so if we look at the static shears, you can see that we divide things into two types. One is direct shear, second one is going to be the torsional shear. So the direct shear, we divide it into double shear, and another one is single shear. So the difference between it's just only the internal force that it react to the action force. For example, like if I put it in the examination, I may give you the diameters of the bowl, and then I may provide you the force P, and then I'm going to ask, I may put these figures, and then I'm going to ask you what is the shear stress of this direct shear. Okay, so you can just find a simple area of the from the diameters, and then you just put the force P over here, and then use your calculators, and then you're going to find the double shear stress. And if you press the shear over here to the wood, if you remember in the lab, so this point is going to be fixed, and then the shear plane that going to occur is just only this plane that parallel to the grain, and you can just find the area of the sample easily by using B over D. So the single shear is also easy. This one is going to be force P divided by A. So A is going to be D multiplied with B. So I'm going to provide you B, D, and P. So you just calculate me the single shear in the exam. All right, and then for another one, we call it torsional shear. So the torsional shear, basically, we use it in the vehicle. We use it in the vehicle most of the time, but in our CE, you may have see this in the futures. You know, when we construct for the ball pile, we use the steel augers over here. So the steel auger over here, they're going to apply the torque, okay, in order to make a hole, the bore hole over here under the ground, in order to cast it as the concrete pile, in order to construct a foundation. Okay, so when we apply the torque over here, we need to check whether if the steel bar is okay to resist the force or not. Okay, so we need to check it with this steel augers. Right, so that's why we need to learn about the torsional shear. Okay, so for the torsional shear, I think we have talked about this in our previous slide. I think in the chapter 3 and 4. So similarly to what I've talked, so there will be some small calculation in the exam. For example, like I would like to find the angle of twist. I provide you guys these parameters, and you guys just note. I'm not gonna give you guys the formulas. So what you guys need to do is you guys need to note the formulas to the one sheet as much as you can, and then you can just calculate the angle of twist and provide me the correct unit of the angle of twist. And then I'm going to ask you for finding the torsional shearing stress. Okay, if you don't know where this come, you can just like go back to the previous video before the midterm, and also the torsional shear strain. So it comes from similar it comes from the same theory that I already explained. And next is going to be the shear stress strain diagram. So basically it's if you learn about torsion, I think torsion you have learned about it already from the lab. Am I right? You guys finished the torsion at the lab already. Okay. So if you experience it already, so this one also going to be in the examination. So I may ask you about this, because in the midterm I use the graph of stress strain curve. So maybe in the final, I also put the shear stress strain curve instead of the normal stress strain curve. And then similarly to the stress strain curve, we need to find the proportional point, ultimate point, and then the fracture point over here. And not all, we need to find the shear modulus. So the shear modulus is basically the delta tau over delta here. And the unit of the strain over here is going to be radian. Okay, just get it. And then it's going to be E over of the material over 2, 1 plus E. I think, and then this one is going to be GPA. Okay, this is the unit. So you can just prove it later. Okay, so what you guys need to know is normally for the torsion, we're going to test it for the circular area. Okay, so what you guys need to do, and most of the student stuck at this examination question is just not able to find the polar moment of inertia. Okay, polar moment of inertia. Okay, so I'm not gonna give you the polar moment of inertia equation. You need to go back and then review it in the chapter 3 or 4, I guess. So I also wrote down for the polar moment of inertia of the circular section, and then you guys just put the radius or maybe the diameters inside, and then you compute for J, and then you can just calculate for everything. Okay, about like 2 or 3 questions. Okay, if you're stuck, you're going to lose point at this point. All right, for the limitation of the test of direct shear, so we have like few points over here, but what I want you to focus is only the point number 1 and point number 2 here. Point number 1, the objective shear strain, most of the time it's going to be the approximate volume due to the small eccentric of the shear force causing the bending stress in the material. Okay, so we're going to look at the bending stress later, and then the friction of the surface, and then the stiffness of the sharpen of the steel plate. So in the exam, I may ask, what is the why the obtained shear strength is an approximate shear strength. So you need to pick the correct one between three of these, okay, in the final exam, right? So this one is going to be the second point. It cannot provide other mechanical properties such as shearing modulus due to no measurement of shearing strain, okay, for the direct shear test. So that's why it's not really that famous. Famous for just only the bowl connection only. And next one is going to be the torsion test. Torsion test, it cannot provide the shear strength of the brittle material correctly since the material failed by tensile test at 45 degrees. So the specimen it's not gonna fail by torsion test, so it failed by shear. It's going to fail by tension stress, not the shear stress. So we cannot find the shear stress from we cannot find shear cannot find shear stress for brittle material by torsion. Okay. Right, next it's going to be similar. So I'm going to ask you guys what are the lab that we test for the direct shear test. We have just only two, or maybe sometime I ask for the material in the exam. So I may ask in direct shear test, what are the material that we test at the lab? So you can just tell me that maybe copper, brass, aluminiums, and wood, or maybe I'm going to give you a tricky answers inside the question. So you guys can just pick four of these for our lab test. Okay, and then these are some machine. So we put the sample over here inside, and then we're trying to pull it by using the steel plate. And then for the wood, we apply the force P over here in order to get the resistant shear stress at the middle over here, the direct shear test. All right, for the torsion test, we have things to consider. For example, like number one, we need to have the sample that light enough to measure the shear strain. Okay, and it also supposed to have the length of the sample long enough in order to uh, reduce the effects of the concentration of the gripping end. Okay, like this point. And then the third one is going to be the thin wall specimen with diameters of the thickness ratio of 10 to 12 maybe to find the proportional shearing strength of the material. Okay, because of when we talk about the torsion, okay, there will be some shift like this. Then when we test for the torsion, most of the time the force is going to apply just only outside surface, which at the center is not related. So the actual resistant force is going to be at the outside diameters over here. It is between these two. All right, for the torsion, similarly, I may ask the lab. So you can just answer lab 4, 10, 11 over here. Okay. Again, this one I already talked in the chapter 4, which for the brittle ductile material under torsion, ductile, and we test for torsion, it failed 90-degree, okay, and then it failed by shear stress, For the brittle under torsion, create 45-degree and fail by tensile. Okay. All right, and then over here. All right, so this is the conclusion table for the test, and then you can just match with this. table by using the figure below. Okay. Next one is going to be the bending test. So for bending test, we have 4 points that we can consider, but what we would like to focus just only the modulus of rupture, which is its strength. Okay, this one is the material strength, modulus of ruptures, and then the flexural modulus of elasticity. Okay, this is the E of bending material. So most of the time we use this in order to find the tensile stress of the brittle material. So in the brittle material, we can just, for example, like concrete, we can just find the bending stress. We can just find the bending stress by using two methods. For example, number one, we call it 3-point loading. The second one, we call it 4-point loading. Just 3-point loading, which means there will be 2 reaction and 1 apply force. And for 4-point loading, it's going to be 2 reaction and 2 apply force over here. So the difference is just only the behavior of the material. For example, if we draw free body diagram over here of the shear of the 3-point loading test, you're going to get the shear of this graph over here like this. Okay, which means this one is going to be shear centers, which means we would like the sample to deform at the centers or would like it to bend at the centers. Okay, but for this one, it's going to be a little bit different. If we draw a shear diagram over here, it can be like go like this, go down, and then constant without having load, because this one P over here is done like this. It's going to be P over 2, P over 2, and over here go down and go up backward. Okay, and for the moment diagram, it's going to be something like this. It's going to be go up over here, go down over here. The maximum is going to be PL over 4. This one is going to be a little bit different for the moment. It's going to be go up like this, constant without having load, and then we have another one is like this. Okay, so it depends on the behaviors of material that we pick. But in our lab, we focus just only the 3-point load because it's a lot more easier for the testing. And we would like to have the maximum deflection at the middle of the sample. Okay. All right, so here's the sample that we test at the lab. We measure force and the delta over here, which is the deformation of the sample. Okay, this is the physical meaning, which means for bending, if we apply the concentration force at the middle of the sample, so there will be elongation occurs at the bottom caused by tension. Force, and the top one is going to produce the contraction that come from the compression force. Okay. All right, so if we look at the flexural formulas over here, we can assume that we look at the stress. This one is called bending stress or ruptures, modulus of ruptures. Sorry, not modulus of ruptures. Flexural ruptures, which is the sigma r, which is equal to my over I. Okay, so we can just find it by m is the internal bending moment, y is the axis from the neutral axis, and I is the moment of inertia. Okay, let's see the second one. If you test at the lab, okay, we test this one. We have cast iron for bending. We have steel, and we have another one is wood, right? So when we test it for the wood, we consider it as the steel and wood. We consider it as the ductile material, but for the cast iron, we consider it as the brittle material. Okay, so the behavior of the brittle material is going to fail like this. For the cast iron, it's going to go up and then fail like this. Okay, we have force and deformation over here, and then this one is going to be the F max. Okay, when this one is going to be the F max, so the equation of the of the modulus of ruptures, it can be found by using this equation, which is equal to 3L over TC squared P failures or F failures. But actually this one is according to these figures, but in the lab we use T equal to B and 2C equal to D. Okay, which means we prove by this equation. So this one change from 2TC power 3 to 1 over 12 BD power 3 over here. And then if we substitute back, for example, if we substitute back, and the C value over here from the lab is going to be D over 2. So it's going to be Mx, it's still, Mx is going to be, in the lab, we're going to apply load at the middle over here by using 3-point loading test, which means the maximum moment is going to be PL over 4 multiply with the C value, which is D over 2 over here, and then divide with the I over here, which is 1 over 12 multiply with 1 over 12 BD power 3. And then if we rearrange the equation in the labs, you're going to get the equation of the modulus of ruptures going to be equal to 3 FL over 2 BD squared. Okay, so in the lab sheet or in the lab manual, you're going to see this equation instead of this, which we're going to use the same equation, which F is going to be for the brittle material, F is going to be the F at failures. Okay, and for the ductile material, we're going to use the same equation, but we're going to use F offset at 0.5 millimeters. So it's going to be in the lab sheet, it's supposed to be 3 F offset offset, and then L divided by 2 BD squared. Okay, and then the F offset or P offset, you can just offset 0.5 over here, and then just find for the modulus of ruptures for the ductile material over here. All right, so if you remember from mechanics of material, we have the simple beam over here. This one is beam, this one is deflection, equation, deflection equation, deflection equation at any point. So we have this maximum deflection for the simple beam with the load at the middle as 3-point loading test at the lab. So if we look at the test, you can see that we plot the P with the deflection, or we plot F with the delta over here. So let's see. From the lab, we test over here like this. We have F, we have delta, and then we're going to plot like curve like this, and then it failed. Okay, so the point over here is going to be the slope over here. So the slope between over here is going to be S slope, or just call it K, equal to delta F over the delta of the deflection. So it's going to be F over delta, but from our theory in this lectures, we use P over V. Okay, all right, from the maximum, from the Vmax equation is going to be equal to PL power 3 divided by 4/8 over here. So if we would like to find P over here, we can just move equation, and then we can just like rearrange the equation equal to P over V over here, which is the slope of the testing at the lab, and then we can just find E easily by equal to L power 3 slope of the testing sample divided by 48i, which I can be measured by the sample dimensions, and K is going to be the slope of the force and deflection of the testing sample at the labs. Okay, but in the lab, you're not going to see something like this. In the lab, you're going to see equation of E equal to PL power 3 over 48 I and delta over here, which delta over here is going to be the deflection of the, oh, this one is going to be F, the deflection of the sample, and then F is going to be the force of the sample. All right. So there's some limitation of the test result from this is the deflection of the beam may be produced by moment only if the beam specimen is a deep beam. Okay, for example, if L over D is less than 10, and for the determining the proportional stress at this test, at the top of the bottom surface, it may subject to the maximum stress with a small yielding. So in case of using the fractional formulas, we need to provide the volume, approximate volume as this equation, which is the my over I or mc over I. Okay, so these are the actual stress on the members, but when we use it in the calculation, we can just simplify it and make it easier to calculate. So we can just make it as the triangle over here. All right. So for the test specimen, we have like two test specimen at the lab. For the first one, it's going to be the short one, and then another one is the long one. When we test it, you're going to observe two different failures. For example, if we would like to avoid the shear failure of the bending of the wood, you can see that the beam specimen should have the length that long enough in the span ratio between 6 to 12. Okay, this one may be asked in the exam, depending on type of material and shape of the specimen that apply the force. But in order to avoid the buckling of the sample, the beam specimen is supposed to have the depth that thick enough, at least like D over B less than 15. You will test it at the lab, so you will see the behaviors. And similarly, I'm going to ask for the bending, what lab are we going to test? You guys can just like answers according to this conclusion. And then we have some notice that you can just go back and read it by yourself. Similarly, we have loading speed, defects, and localized yielding stress. So it's going to be similar. And then you can see that the flexural modulus of elasticity E is close to the obtained from the tension test and the compression test. So E over here is come from the same source, which means you can just compare with another labs after you test it for the bending. You also can compare it with the compression and tension too. Okay. All right. Okay. So if we look at the cast iron and the concrete is going to fail similarly, we call it underbending. We call it the rupture failures for when we test it for the bending. Okay. The rupture failure is the immediate failure without warning any deformation. For example, like that's why in the beam, like the reinforcement beam, we need to put the steel inside in order to have some warning. Okay, when the beam is going to fail, like the reinforced concrete beam is going to fail, which means it's going to produce some warning for you to see the crack of the steel first. Otherwise, if there's no warning, for example, like this surface of the cast iron, when it fails immediately, the bedding is going to be collapsed. So that's why that sudden failures, we call it the immediate failures. It come from the brittle materials such as the concrete and the cast iron. But the ductile failures is going to behave differently. For example, for failure of the timbers, we have like 6 failures of the timbers. For example, that we usually see is the simple tension. When we apply the force on top, if it's long, it's going to break like this. We call it simple tension. And this one, I never seen it before. We call it splintering tension. It's going to fail like this, but I don't know how can it fail like this. Maybe because of it grain. But for the compression, it can be happen. When we apply the force, it can be happen like this. And then the cross grain tension, I think I've seen this in the lab before. And then the brush tension. And lastly, it's going to be, I think, the A and F mostly seen in the lab. Okay, if you would like to see it in detail, you can just read from here. So this may also ask in the examination. I may put some image over here, and then I may ask, what is this mechanical failures of the timber sample? So you need to answer the simple tension, something like this, okay, in the exam. All right, so this is the image from the lab. Okay, so this one is the shear failures, and this one is going to be the simple tension failures. Okay, but for the ductile steel, you cannot break the ductile material such as steel for testing bending. But the thing that happened to it is we call as the we call it the plastic hinge. What is plastic hinge? So why in the brittle material we don't have plastic hinge? Plastic hinge is the behaviors of the ductile material when applying small force. It's going to provide you a really large deformation. You apply small force, it's going to produce a lot of deformation. That's one we call plastic hinge. The plastic hinge uh, occurs when it reaches the plastic moment over here. Okay, or if we just put say in short, we can just say it as the yielding point. Okay, when it reaches yielding point, it's going to have the plastic moment, and then it's going to produce the plastic hinge inside. So the black one over here. And when you apply small load, so there will be a lot of deformation after it reaching the yielding point of the specimen over here. Right, so this is the sample, the iron, and there are some factors that affects to here, so you can just read it later. Okay, and then we have specimen dimension, so it can be shape of the beam section, size of the beam section over here. And this one is from, I think this image from Achansi Desai Labs in USA. And then he took some picture over here, and then the experiments on the really thin web over here, thin over here, thin plate over here on top, which means it's not gonna produce a lot of uh, a resistant force. So this one is not gonna be in the exam. So just for the case study over here. All right. Okay, so just skip it and then move it to the final point, which is the fatigue. Okay, so fatigue, I think we have talked about this like in the chapter 4 a lot, which is the one that also in the examination. So fatigue is going to be the one we call it repeat applying load or stress. Okay, and the repeat applying load or stress, it can be count as a cycle. Okay, or we call it cyclic loading. So the cyclic loading, which means you're going to apply the force, release, apply the force, release in the cycle like this. Okay, and what we measures from the fatigue over here is simulate from the bridge and the crane design, which means crane, they need to lift some equipment and then need to release it. So the crane is going to experience the same lift some load, release, lift, get some load on, and then release, and also similar to the bridge. When you drive your motorcycle or car past the bridge, so there will be some load on the bridge, and then when you drive past the bridge, it's going to have the zero load, which means we're going to apply and then release, loading and release. And then after that, you're going to get the load in cyclic like this or in cycle like this, and then we count by stress and number of cycles as an N curve, and then we plot it like this. Okay, so in this point, what I want you to I may trick you in the exam, so I may give you the question of which one is not correct about applying fatigue stress. Okay, So it can be like stress at the test equal to stress ultimate, or the second B test equal to 0.5 ultimate, something like this, like 0.4 stress ultimate, 0.3 whatsoever. Just put it here. Which means what I want you to focus is when we test for the fatigue, we're not gonna test it at its ultimate. Okay, you need to test it at least below the ultimate, around like 0.8, or sometimes can be goes up to 0.9 of the ultimate. So if I ask you which one is not correct, the stress at testing is supposed to be not equal to the ultimate of the stress. Okay, which means the stress that we test supposed to be less than ultimate, and the strain that occurs supposed to be lower than the strain ultimate. Okay, and these are the example of failures by fatigue over here. But most of the time it's not failed by the members. Most of the time it failed by connection, the bowl and maybe the welding of the connection. So that's why it failed like this. Okay, so in order to calculate the cyclic load, so we can just find the mean stress over here, stress amplitude, and then stress range. So I may just give you some point over here, stress max, and then stress mean. So this one you need to set, when you test the sample, you need to know what is the stress, and then you need to set in the machine what is the stress max and stress mean. Okay, but for our lab, I think we set the stress max and then the stress mean equal to 0. Okay, because in our lab we would like to pull the sample just only in tension only. Okay, but for some application like cast iron, I think they need to test for both compression and tension. That's why they can reduce the stress minimum for the compression, and then if they pull it out on top, it's going to be for the tension, and then we can just calculate it. And there we go. If, for example, in for the aluminum that used to build the airplane wings, so they set the maximum stress over here, and then we can just calculate by 10, and then the minimum is at -2. So we can just put it here, which means the average or the mean equal to 4 megapascal, and then the amplitude is going to be 6 megapascal, and the stress range equal to 12 MPa. All right, so if you remember this from the test, we have the sample like this. We have sample like this, put it in, and then we try to pull the sample up. The aluminum force P, people may give you to test at 50, 60, 70, and then the final result that you're going to get is going to be the graph between the log graph between n from number of cycle, the one that in the digital monitors that you can count from the machine, and then the stress that you applied, you can just by S over here. So after you apply many points, and then you're going to get the line over here. So the important note over here of the SN curve, the stress and number of cycle curve, is just only the larger you go close to the ultimate, the smaller of the cycle you're going to get, the number of cycle you get, which means you apply smaller stress to the sample for testing fatigue, the life cycle is going to be a lot larger. It's just because when you apply the large force, the sample is going to lose its area of resistance faster. Okay, but at some point it's not gonna lose anything. That point we call it endurance limits. Okay, so let's see how we calculate for the endurance limits. For the endurance limit is the point that even though you apply how many time of the cyclic load, your sample is not gonna fail by fatigue. Okay, most of the time it's in between 0.4 to 0.5 sigma ultimate, right? So it's not 0.4 to 0.5 yielding, it's 0.4 to 0.5 of the ultimate. Okay, so for example, like if I go back to this steel and I would like to calculate for the SS490 right here, for example, like in the examination, I may provide you this table, and then I said, okay, I would like to check whether if my sample will be higher or lower than the endurance limit if I use it to construct the beam for the railway. So for the railway, so this one is going to be, we have for SS490, I'm going to get yielding stress equal to 285, okay, MPa. And then I'm going to have the allowable. So when we design, okay, we're going to use only yielding, okay. So when we design, we use yielding, we have allowable. For example, if the factor of safety is going to be equal to 2, so it's going to be 285 divided by 2, it's equal to 142.5 MPa over here, okay. And then I know that the endurance limit of the steel is going to be the 0.4 stress endurance equal to 0.4, like a really low one, 0.4 multiplied with tensile stress. The minimum is 490, so 490. So 490 multiplied with 4904, so it's 196 over here MPa, which means this one is larger than sigma allow. So there will be no fatigue occurs to my beam for the grade of SS490. So in the examination, I may ask, okay, ask you to pick one of the steel classification according to the TAS 1227, okay, and then ask you to calculate for the sigma endurance for me, and then check whether if this one larger or lower than the sigma allow. Okay, so these are some design example similar to what I just explained over here. Okay, and I'm going to provide you the factor of safety and then the ratio of the endurance limits, and then you need to calculate for just only the sigma allow and the endurance stress. All right, last one is going to be the one that we have talked, is the aluminum. So for the aluminum, there's no endurance limits, which means we need to test it and then need to provide a really high factor of safety. And then if it reaches the one that we can accept it, we need to replace the material by a new one immediately. So all right, so these are the conclusion over here, and nothing more to focus. You can just go back and read similarly what lab that we test for this, and then the limitation of the test I already explained from the chapter 4 over here, and that's it for the chapter 5. Okay, do you have any questions? All right, if no, thank you for coming today, and see you at the labs on Thursday.